Calculation of moment of inertia of rigid body. The moment of inertia of a point mass with respect to the given axis is defined as I is equal to m into r square. R is the perpendicular distance of the point object from the axis given. This is the given axis. This is the perpendicular distance. This is a scalar quantity in the realm of the +2 stage, the realm of IIT-JEE. And the unit of mass is kg, unit of the distance of the particle from the axis is meter. Therefore, the unit of the moment of inertia is kg meter square in MCAS unit. This is for a particle or the system of particles. Suppose we have another particle m dash and this distance is r dash. Its moment of inertia about the given axis can be written as m dash r dash square. If you take so many particles, a group of particles, m1, m2, m3, m4. This is the given axis. This mass is at a distance of r1, m2 is at a distance of r2, m3 is at a distance of r3, m4 is at a distance of r4, and so on. Find moment of inertia about the given axis. So, moment of inertia is a scalar quantity. So, the net moment of inertia is equal to moment of inertia of the first particle, of the second particle, of the third particle, of the fourth particle. All the moments of inertia, you just add I1 is equal to m1 r1 square, I2 equal to m2 r2 square, I3 equal to m3 r3 square, and I4 equal to m4 r4 square. If there are so many particles, then you have to go on adding up to the nth particle. Therefore, for a group of particles, the moment of inertia can be written as sigma mi ri square, where ri is the perpendicular distance of the ith particle of ith particle from the given axis. So r should be the distance of the point object from the given axis, and that distance should be perpendicular to the axis. So to calculate the moment of inertia, we have to give the axis about which we are interested in calculating the moment of inertia. Let us find the moment of inertia of a pendulum bob. Moment of inertia of the pendulum bob, which is hanging from this point by an inextensible thread of length L. So we can draw so many axes, countless straight lines through this point. Let us take this axis. Let us take this axis. Let us take this axis. We have taken three axes: x-axis, y-axis, and z-axis. We need to calculate moment of inertia about x-axis, moment of inertia about y-axis, moment of inertia about z-axis. For x-axis, this is the perpendicular distance, let it be r1. For y-axis, this is the perpendicular distance, that is r2. For z-axis, the perpendicular distance is r3, that is none other than the length of the string. Therefore, Ix is equal to m r1 square, Iy is equal to m r2 square, Iz is equal to m r3 square. R1 is equal to, if this is the theta, R1 can be written as L cos theta. R2 is written as L sin theta. This is equal to L sin theta, and R3 is equal to L. Therefore, the moment of inertia about x-axis is equal to m L square cos square theta, but not m L square. Don't write blindly. Moment of inertia is m L square. R2 is equal to L sin theta. Therefore, moment of inertia about the y-axis is equal to m L square sin square theta, but not m L square. Now about z-axis, you take z direction. About the z-axis, the moment of inertia will be equal to m r3. R3 is the perpendicular axis, perpendicular distance from the axis, that is none other than the length of the string in this case. So R3 is equal to L. In this case, it is ml square. Iz is equal to ml square. Iy and ix will not be equal to ml square. Ix is ml square into cos square theta. Iy is ml square into sin square theta, whereas Iz is equal to ml square. Therefore, when you want to calculate the moment of inertia of a point mass, you need to mention the axis about which you are interested in calculating the moment of inertia, provided that the distance of the particle from the reference axis is known, mass of the particle is known, then only you can calculate the moment of inertia. Now the question arises, when this pendulum bob is released from rest from the horizontal, it swings. When it swings, find its moment of inertia. When it swings, it is swinging or it is revolving about the horizontal axis. So here the axis for swinging bob, axis is z-axis. So in this case, the moment of inertia is equal to ml square, because Iz is ml square. Sometimes they may ask you, if the bob is revolving in circular path in horizontal plane, you need to understand when the plane is horizontal, the circular plane is horizontal. This is the axis of rotation now. And here the axis of rotation is z axis. Here the axis of rotation of the string is z axis. Here the axis of rotation is y axis. So here the moment of inertia will be equal to Iy is equal to ml cos theta square of this ml square cos square theta. So from physical condition we have to understand, we have to analyze about which axis the string is revolving. About that axis, the moment of inertia you have to calculate. So this is the technique in calculating the moment of inertia for a single particle or group of particles. Well, let us calculate the moment of inertia of two particles connected by a light rigid rod about the center of mass axis perpendicular to the rod. This is the axis y dash. Let it be r1 and this is r2, and the length of the rod is given as L, or you can write R. This is M1, this is M2. Moment of inertia of the system with respect to the center of mass is how much? For this, let us solve. Moment of inertia as per the definition of the system of particles about the given axis is equal to mi ri square summation of this factor. So it is m1 r1 square plus m2 r2 square. R1 and r2 are the perpendicular distance of these particles from the given axis. I see. Where m1 r1 is equal to m2 r2 about center of mass, because position vector of the center of mass with respect to itself is equal to mass 1 into its position with respect to center of mass, that is r1 vector, plus this mass m2 into its position with respect to the center of mass, that is r2 vector, in this direction by m1 plus m2. Since RCC is 0, the position vector of the center of mass with respect to itself is 0, we can write m1 r1 plus m2 r2 is equal to 0. So m1 r1 is equal to m2 r2, or you can just write m1 r1 vector equal to minus of m2 r2 vector. If you take the magnitude, you are getting m1 r1 is equal to m2 r2, or you can write For R1 you can just write minus R1 I cap. For R2 you can write plus R2 I cap if this is x direction by M1 plus M2 equal to 0 to get the same answer. Therefore, we can write M1 R1 is equal to M2 R2 and R1 plus R2 is equal to R. Using these three expressions, expression 1, expression 2 and expression 3, we can get the answer. Or when you are using these two expressions 2 and 3, using this 2 you can get R1 is equal to, by using equations 2 and 3, we have R1 is equal to M2 by M1 plus M2 into R and R2 is equal to M1 R by M1 plus M2. Now substitute R1 and R2 in the equation 1 to get IC is equal to M1 into M2R by M1 plus M2 square of this plus M2 R2 is M1R by M1 plus M2 square of this, and after simplification you are getting IC is equal to M1 M2 by M1 plus M2 into R square, and this is again the reduced mass. Therefore, IC is equal to reduced mass times the distance of separation square of that. This expression is valid for two particle system. Let us now calculate the moment of inertia of the rigid body, which are in general assumed to be uniform about the axis passing through the center of mass, or sometimes some other points. Let us calculate the moment of inertia of some rigid bodies after finding the moment of inertia of the system of particles where the particles do not touch each other. That is called discrete particle system. Now, the continuously arranged particles of the rigid body. Let us take the example of a rod. The uniform rod about the center of mass axis. Let us assume that mass of the rod is m and its length is L. So, you take the axis which passes through the midpoint of the rod. You consider this as the center of the rod or the origin of the coordinate system. This x is the y-axis. With respect to this origin, this is L by 2 and this is minus L by 2. Therefore, for the continuous mass distribution, the moment of inertia about the center of mass can be written as r square dm, the integral or integration of this. Take a small segment at a distance of x and the thickness of the small segment, let it be dx. So, dm is equal to total mass of the rod by the total length into dx. This condition is valid for uniform object, uniform rod. Sometimes we call this linear mass density, which is defined as mass of a small portion upon its length. This is called linear mass density given by lambda or sometimes mu in some books. Mu is not the coefficient of friction here. We can use the symbol mu for linear mass density, or lambda also you can use. dm by dl for uniform and non-uniform mass distribution. And you can write total mass by total length is equal lambda for uniform mass distribution, but not non-uniform mass distribution. Therefore, you can accept this formula as the common formula or common case for both the cases of uniform and non-uniform mass distribution. R square dm. dm can be written as lambda dl. dl can be written as dr. So this is lambda r square dr. For uniform rod, lambda is a constant quantity. For uniform rod, lambda is constant. Then only you can pull it out of the integral. Then IC can be written as lambda r square dr. Here r can be written as x. If you like r, you can put it, or if you do not like, write as x square dx. X ranges from minus L by 2 to plus L by 2. This will be equal to, after evaluating the integral, you can write this is x cube by 3 from minus L by 2 to plus L by 2. This gives us IC is equal to ml square by 12. About the axis which passes through the center of mass of the rod or midpoint of the rod for uniform rod and must be perpendicular either this axis or this axis. Sometimes we are asked to calculate the moment of inertia of the rod, not about the center of mass axis, but about any other axis perpendicular to the rod or normal to the rod, but different point other than the center of mass. Let us take the end point P, suppose. In this case, directly you can take the small segment of mass dm at a distance of x. dm is equal to lambda dx. The moment of inertia of the small segment, it behaves as a particle about this axis, say z axis. Moment of inertia can be written as r square dm or x square dm. Here dm is equal to lambda x, lambda dx. So lambda x square dx. So lambda x cube by 3 if you integrate it. Here we can change the lower limit and upper limit. X ranges from 0 to x is equal to L. So 0 to L, 0 to L. So you are getting lambda L cube by 3. But what is lambda? M by L for uniform object. For uniform object, lambda is M by L. L cube by 3. So you are getting ml square by 3. That is the moment of inertia of the rod about one of its end. However, you can calculate the moment of inertia of the rod about any point. The axis passing through any point, but the axis must be perpendicular to the rod. Sometimes you take the rod and they will give the axis here, z axis. This is L by 3, this is 12 by 3. Up to this expression you are getting. Take small segment dm at a distance of x. So its moment of inertia about this axis, or about the z axis, or about the y axis, is equal to x square dm, and integrate it. Total mass is m, total length is L. For uniform rod, dm can be written as lambda into dx. Lambda is equal to total mass by total length for this particular uniform case into dx. X ranges from minus L by 3 to plus 12 by 3. So you are getting m by L into x cube by 3 minus L by 3 to 12 by 3. So m by L take common. 1 by 3 also you can take common. X cube can be written as 12 by 3 the whole cube minus the lower limit, you can put minus L by 3 cube of this. The cube of 1 by 3 is 1 by 27. So m by L 3 into 1 by 27 take common. You can take L cube also common. So you are getting cube of 2, that is 8, minus cube of minus 1, that is minus 1. So you are getting 8 minus minus 1 is 9. 9 in the numerator will get cancelled with 9 in the denominator, and L in the denominator will be cancelled with L in the numerator. So in numerator we are getting L square. So m L square 9 by 81, that will be equal to 9. So this is the answer. So using the basic principle x square dm integral, you can calculate the moment of inertia about any axis, but must be perpendicular to the rod passing through any point of the rod. Or sometimes the axis can pass through a point, but axis can lie outside the rod also. In this case, you take a point like this. This is the axis. Here this is L or L by 2, or you can take L and this is L. You can take x equal to 0 this point. This is y axis, this is x axis. How to calculate the moment of inertia of the rod about y-axis or about z-axis? Take an element at a distance of x. Its moment of inertia about y or z-axis is equal to x square dm. Integrate it. Dm is equal to total mass by total length of the rod into dx. Integration of this. M by L, take it out. X square dx integral will be equal to M by L x cube by 3. Here x ranges from L to L plus L to L. So the lower limit will be L, upper will be 2L, L to L. Like this. Next, you just evaluate it. 2L cube of this minus cube of L. This will be 7 L cube by L, that is 7 L square. So 7 ml square by 3 will be the answer. So these are all the problems we are doing based upon the uniformity of the rod. Number 1 condition. Number 2 condition is the axis must be perpendicular to the rod. Either this is y-axis or this is z-axis. If the axis is not perpendicular, then how to solve the problem? Suppose the rod is like this, and you are required to calculate the moment of inertia of the rod about this axis, which is not perpendicular to the rod, and about z-axis, fine. The moment of inertia of the rod about z-axis, because z-axis is perpendicular to the rod, will be equal to ml square by 3. But when the rod makes an angle theta with respect to y-axis, this is the reference axis. How to calculate the moment of inertia of the rod about y-axis? But this is not equal to ml square by 3. Then how much it will be? Let us use the basics. We states that moment of inertia of a point of mass dm about the given axis is given as dm into r square. If you integrate it, you are getting the moment of inertia of the entire system, the rod, about y-axis. Here r is equal to you can take this is x, r is equal to x sin theta square of this. Sin square theta is a common constant quantity, take it out of the integral, and we are getting x square dm. This length is L, and the elementary segment has length dx. Putting dm is equal to total mass by total length into dx, we can get sin square theta into the integral x square m by L into dx. X ranges from 0, x we are calculating from here, 0 to the length of the rod. You are getting L m by L sin square theta x cube by 3 0 to L. So finally we are getting ml square by 3 sin square theta, an additional factor is coming. It is not ml square by 3 but ml square by 3 sin square theta. That's interesting. You take the axis, passing through the center of mass, and this is theta. Here the moment of inertia you can prove through the center of mass is equal to ml square by 12 sin square theta, but not sin theta, sin square theta. That you can try. And this is the center of mass. However, moment of inertia of the same rod about z-axis, where z-axis is perpendicular to the rod, will be equal to ml square by 3. And about the x-axis, instead of this will be the angle phi, will be equal to ml square by 3 sin square phi, or it will be cos square theta. So about 3 different axes, the moment of inertia of the same rod will be different. Therefore, the moment of inertia depends upon the reference axis. Not only that, when the rod is not uniform, the moment of inertia also depends upon the mass distribution, which is characterized by linear mass density of the rod. In the next problem we are going to discuss it. Let us take the non-uniform rod whose density varies with respect to the length along the x direction. Along x, let its density, linear mass density, varies linearly, given by this equation. Lambda is equal to lambda naught. Lambda naught is a constant quantity, that is the linear mass density of the rod at the origin. Lambda naught into 1 plus x upon L. X is the variable, L is the length of the rod. Here you have to calculate the moment of inertia of the rod about z-axis or y-axis passing through this point O. Iz is equal to x square dm, and dm is equal to lambda dx. Lambda x square dx. Since lambda is not uniform, you cannot take it out of the integral. Here you have to substitute the value of lambda as lambda naught 1 plus x by L. That is lambda into x square dx. Lambda naught is a constant quantity. Pull it out of the integral. When you open the bracket, you are getting x square plus x cube upon L dx. X ranges from 0 to L is equal to lambda naught, that is the integral of x square is x cube upon 3. The integral of x cube is equal to x4 upon 4. L will be there, 0 to L. So you are getting lambda naught L cube by 3 plus this will be equal to lambda naught into L cube by 3 plus, when you put L here, L4 by 4L, that is L cube by 4 is equal to 7 lambda naught L cube by 12. Answer.